Okay, perfect. We're going to look at the renin, angiotensin, aldosterone system, as it says. That there, yeah. Okay. So this is process in the kidneys. It starts essentially when we've got a drop in blood volume, so blood pressure drops. Usually if you have like a massive hemorrhage, so I don't know if your arm's fallen off, this is quite like an extreme sort of hemostasis, trying to get blood volume and blood pressure back up. Okay, so we'll start off, so it's renin, angiotensin, aldosterone, and it's in that order, so it happens in that order. So to start off with, let's go up to our, in our kidney, we know our Bowman's capsule, our afferent arterial, the wider one, our efferent, the narrower one, and it goes into the PCT, our proximal convoluted tubule, through our loop of Henle, up to our distal convoluted tubule, and then the collecting duct, which I haven't drawn on here. Okay, so important thing we're gonna look at is how we identify we've got a low blood pressure, or how our kidney identifies that we've got a hemorrhage or low blood volume or blood pressure. Okay, so we've got these receptors, or these cells, which have receptors. So in our distal convoluted tubule, it's hard to see because I've got the orange pen, but in our distal convoluted tubule, okay, let's rewind a little bit. So here we can see our afferent arterial and our distal convoluted tubule. They're very, very close together, and they're actually connected to each other via connective tissue. Okay, so these are quite close, and that's important to remember in a minute, that they're very close to each other so they can communicate. Okay, so in our afferent arterial, we have these cells that line the walls of the arterial. Okay, these are juxtaglomerular cells. They're also known as granular cells, and these are the cells that release our renin. So these have baroreceptors on them. So all of these cells, they have little receptors on them, and these receptors, baroreceptors, they detect blood pressure changes. So if it drops, this is going to detect that change, and that's what releases the renin. So we've got 3 triggers for renin release. Okay. Don't need the term. Okay. Got 3 triggers. We've got a drop in blood pressure, so that'll be noticed by our baroreceptors. So our granular cells, they'll detect our drop in blood pressure. We've also got sympathetic nervous system innervation. So if your arm's been chopped off, you're likely going to have sympathetic nervous system activation, that fight or flight. At that point, you're pretty screwed anyway, but you'll have it anyway. So you'll have sympathetic innervation, and what this does is it innervates our granular cells and stimulates them to release renin. Okay, so that's another thing that causes renin to be released. And then our third trigger is, if we need to think about this a little bit, but if we've got a reduced blood pressure, so that means the blood coming into our Bowman's capsule, into our glomerulus, is going to be less. It's going to be reduced. So what happens is, this blood, because if we remember back to A level, where our osmotic pressure coming back in has to overcome our hydrostatic pressure, or the other way around. So our hydrostatic pressure, which comes from our blood pressure, our high blood pressure, it has to overcome this osmotic tendency for blood to come back into the arterioles. But if we've got a reduced blood pressure, that means osmotic pressure is going to be greater than hydrostatic pressure. So blood isn't going to leave in this glomerulus. It's not going to come in to our collecting duct and our nephron. So that's important to bear in mind. Reduced blood pressure means less blood is coming through this nephron system. If less blood is coming through, that means it's going at a slower rate. So think of blood pressure like voltage. If you've got a lower voltage, you've got less oomph pushing that blood along, pushing that current along. So it's going to go along here, along our PCT and loop of Henle, much slower. So why does that matter? If it's going along slower, that means all this sodium that comes out of our nephron, it's got time to be reabsorbed. So although it's being kicked out a little bit, most of it is going to be inside our nephron. So when we get to the point here in our distal convoluted tubule, we're going to have more sodium than we should. Okay? So sodium, think about this like this. Wherever our sodium goes, due to osmosis, water will follow. Okay? So we want more sodium to be outside this nephron, because everything in this nephron is going to be urinated out. That's going to go. We don't want to lose any liquid. So we want sodium to come back into this medulla, into the medulla. I forgot the word for it then. Okay. So this is a trigger. So what happens is we've got some cells. So I mentioned we've got this connective tissue between our afferent arteriole and our distal convoluted tubule. So along this border, we've got some macular denser cells, okay, in pink here. And what they do is they detect, so I spoke about this sodium, they detect the fact that there's more sodium in the cell, in the collecting duct or the distal convoluted tubule than out, or more in there than there should be. So what this does is it sends a little message. It goes across this connective tissue and sends a message to our granular cells and tells it to secrete more renin. Okay. So 3 ways renin is secreted, which is important. This is the first step of our little cascade that we've got. So renin goes out through this system, comes out through the afferent arteriole, and suddenly if we come over here, we've got our little kidney, and it's going to come out. So renin's now going to enter our systemic bloodstream, so our main bloodstream, and it's going to interact with everything in there. Okay. So something else to bear in mind now. It's now in our main. We've got renin in our main bloodstream. We're gonna find. So we've done renin. We've checked that one off. We want angiotensin. So where is angiotensin made from? It comes from. So it comes from the liver. Okay, it's in the liver, and it gets secreted in our blood into our bloodstream. But when it's in the liver, it's in an inactive form. It's called angiotensinogen. Okay. So again, this ogen means it's inactive, just like any if you think like pepsin, just that's its inactive form. Okay. So when it comes out of the liver in its inactive form and enters the systemic circulation. And what happens is renin comes along and interacts with it. So renin, let's bear in mind, renin is an enzyme. So renin comes along and snips this ogen off. So it activates it. So we've now got active angiotensin. So that's angiotensin 1. Okay. Angiotensin 1 is now floating around in our bloodstream, and this is active. Angiotensin 1, not really clinically relevant, but it does cause a little bit of vasoconstriction, but it's not the main thing we look for. That's irrelevant, really. Okay, so we've got angiotensin 1, that's going around in the blood, and it comes across our lungs, all right? It'll eventually come across our lungs, and in our lungs, we've got an enzyme that's made, and this is called angiotensin converting enzyme, ACE. Okay, so you probably think, well, ACE inhibitors, I imagine that's what that is, but I don't know what an ACE inhibitor is yet. Okay, so we've got ACE. What we do know is that ACE interacts with angiotensin 1. So in the name, angiotensin converting enzyme, it converts angiotensin 1 to angiotensin 2. Okay? So this is our final sort of, not our final one, but it's our next compound thing in our system. Okay? So renin, angiotensin, check. Aldosterone system. Okay, so what does this do? So angiotensin 2, generally it's a vasoconstrictor, so it just generalized vasoconstriction. So what's that going to affect if we have vessels constricting? That's going to have more increased blood pressure essentially, okay, which we know. Okay, increased blood pressure. Specifically then, we're going to have constriction of our efferent arterial. So if we look back at our efferent arterial, okay, so if this is constricting, so we've got our smooth muscle, and that's going to constrict our efferent arterial. So that's going to be narrower now. Okay, what's that going to mean? That's going to mean increased blood pressure, which we know. We know vasoconstriction increases blood pressure. But specifically in this context, if we're decreasing the diameter of our efferent arterial, that means the pressure in our glomerulus is going to increase. Okay, so that's good. If we've got an increase in glomerulus pressure, that means we've got this hydrostatic pressure again. We've got this high hydrostatic pressure, which can overcome this osmotic pressure, putting blood back into our vessels. So suddenly, we've got more blood coming through our nephron. Okay, so glomerular filtrate rate increases, so more blood is coming through our nephron. So that means, if we think back to our sodium, if it's going faster, that means more sodium is going to be outside in the medulla. Okay, so more sodium is now going to be in the medulla. So wherever sodium goes, water follows. Okay, so we've now got water coming out of the medulla. Okay, in this negative feedback loop as well. So remember, our macular denser cells are the ones that identified this increased sodium level in the distal convoluted tubule. So it's sort of like negative feedback here, where actually sodium is now leaving the distal convoluted tubule to retain all that water. We don't want it to go and be ejected in our urine. We want that to stay in our bloodstream. So it's going to be reabsorbed in our kidney, in this sort of pelvis. Sorry, not in this pelvis. It'll be reabsorbed into our collecting ducts in our distal. No, ignore that. It's going to be reabsorbed into our bloodstream. Okay. So increased blood volume, because more water and more liquid is coming back into our bloodstream. Increased blood volume means an increase in blood pressure. Okay, also good. Alright, what else does angiotensin do? So angiotensin, it goes to two places now. So the first place I'll talk about is it goes to our, let me just find a pen. It goes to our adrenal gland. Okay, so it goes to our adrenal gland, which sits just above the kidney. It's like its little hat. So, and it goes specifically to the cortex of the adrenal gland. So that's sort of the outermost layer of our adrenal gland. And this is where aldosterone is found, okay? So aldosterone is in this area here, in this cortex. So that when angiotensin 2 comes to our cortex of our adrenal gland, it releases aldosterone. Aldosterone now goes to our distal convoluted tubule, which, if we think about it in terms of this, it just goes in here to our kidney, because our adrenal gland is on top of our kidney. It goes to our distal convoluted tubule, and what it does is it tells our distal convoluted tubule to absorb more sodium, okay? So, even more so, it stimulates sodium to go into our medulla, okay? So more sodium goes into our medulla, more water goes into our medulla, and then it can be reabsorbed back into our arterioles and blood vessels. Okay, so it stimulates that process even more so. So again, increased blood volume means an increased blood pressure. Okay, which is what we're trying to do, because we've just lost a lot of blood with this hemorrhage, with our arm falling off. We need to get that blood pressure up again. Otherwise, if we link back to our cardiac output, we're going to have reduced cardiac output and potentially cardiac problems. Okay. Where else does the angiotensin go to? It goes to our brain. Okay. So when it goes to our brain, specifically our posterior pituitary gland, it stimulates ADH to be secreted. So we know what ADH does. It goes to our collecting duct walls, our distal convoluted tubule walls, and makes it more permeable to water, so all those aquaporins binding with the wall, and allowing water to be reabsorbed back into our bloodstream. So again, more water is being reabsorbed, increased blood volume, increased blood pressure. Okay, so that's important. That's that. So all these processes, all these things, all this angiotensin 2, main action is to increase blood pressure, increase blood volume, and reduce the amount of urine we're excreting. Okay, so now we've checked off aldosterone, and that's it basically. That's our renin angiotensin aldosterone system.